Okay, folks, welcome back. This is section 5-2. This is recording number 3. We left off here talking about the variance and standard deviation. Now, I want to re-emphasize, at the risk of belaboring this point, you have to make sure you understand these concepts are similar, but they are different from the concepts that we talked about in Chapter 3. In Chapter 3, we were talking about the measures of central tendency, measures of dispersion, things of that sort. Those concepts were with respect to frequency distributions. In other words, actual measurements, actual data points. Now here in Chapter 5, we're talking about very similar concepts. We use the exact same terminology, the same nomenclature. However, we're talking about probability distributions. And I would say the key difference is that in Chapter 5, when we're talking about probability distributions, a probability distribution is talking about the probability of certain things occurring, certain outcomes. So it's something that has not happened yet. It's something that we are predicting, we are guessing is going to happen. So that's what the author is talking about when he talks about long run or theoretical. What he's basically saying is this is what we expect to have happen, but it hasn't happened yet, and it may never happen. I can have a probability distribution for flipping a coin and never flip the coin. Whereas when I was talking about it before in Chapter 3 for a frequency distribution, I was talking about actual data points, actual measurements. So I hope that helps explain the distinction here. So here we are in Chapter 5 now, and this is, as I said, section 5-2. Now we're going to talk about variance and standard deviation. So as the author says here, for a probability distribution, the mean of the random variable describes a measure of the central tendency. That's the measure of the so-called long run or theoretical average. That's what how he's referring to the situation where this is our best guess. We don't actually do the experiment. And as the author points out, it does not tell you anything about the spread of the distribution. So hopefully you remember from Chapter 3, we talked about how we many times want to know how much variance is there, how much spread is there in the data points in Chapter 3. That was an example we use of the paint. How good a job did the paint do? The mean of the different brands, of the two different brands, the mean could stay the same, but the variance was so much different that the two brands weren't very comparable, that one of them was a much better brand in that sense. Okay, so what he's trying to do here is trying to say here that from Chapter 3, we measured the spread, we measured this variability, we use a concept called variance and standard deviation. And these are the formulas that we used. Now, if you look at these, hopefully you did some of those problems and you kind of have an idea of what it's all about. The concept behind the variance and standard deviation is that it's the average deviation is what it boils down to. This summation of x take away mu. Well, mu is the mean of the frequency distribution. Remember, this is from Chapter 3. This is what we did in Chapter 3. So x subtract mu, that's the deviation of each of these data points, x sub 1, x sub 2, x sub 3. So x take away mu, we square it because we want to get rid of the negative signs. We add them up. That's what the symbol here means. This is the sigma symbol. So it means add them all up, and then we divide by the number of data points that are in the population. Well, when we do something like that, when we add and then divide by the number of data points, that's just the mean. So this is the mean of the deviations. Now, we don't call it that. We call it, and I'm sorry, it's the mean of the deviation square, okay? The mean of the deviations squared. Or sometimes people will say the mean of the square deviations. We don't typically call it that. We typically refer to this as the variance. But then we have the standard deviation. The standard deviation is the square root of the variance. Now this one, the language is a little more clear. For this guy right here, it's very common to refer to that as the root mean square. Engineers will use that expression all the time. The root mean square is the root, that's the square root, then of the mean of the square of the deviations. So that language is actually a little more clear after you take the terminology apart. So this one you'll see referred to as the root mean square sometimes. Okay, so in any event, what he's trying to contrast here now. Chapter 3, this is what we did. It was for a sample or for a population. These formulas cannot be used for a random variable of a probability distribution because our concept here is that n is infinite. Okay, we're doing this experiment an infinite number of times. So the variance and standard deviation, it wouldn't make any sense to use this formula. So we have to use a different type of a formula. We compute it differently. Okay, so to find the variance, here's how you do the variance. And then remember, the standard deviation is just the square root of the variance. So once you have the variance, you have the standard deviation. So to find the variance for the random variable of a probability distribution, here's what you do. You take this is a summation sign, so you're summing all of these dudes here, all of these data points. X subtract mu, that quantity is squared, times the probability of that particular data point. So it's X. It's a little bit unfortunate. I wish the author would use the more sophisticated notation here. Normally, what we'll say here is we'll say X, and then we'll have I equals 1 to N, and then it'll be N on top, and then it's X sub I. I think that makes it more clear that what we're really doing is we're adding up each of these data points, X sub 1, X sub 2, X sub 3, X sub 4, etc., etc. I think it would be more clear to you, even though that notation is a little bit harder to get your arms around. Once you understand that notation, I think it's more clear. In any event, you take each one of these data points, you subtract it's X subtract mu, you square that to get rid of those negative signs, then you multiply it by the probability of that particular data point. Okay, that gives you a term. When you add things, you call each of the things that you're adding, those are called terms. So that gives you a term. Then you do the next one. So it's X sub 2 subtract mu, quantity squared, times the probability of X sub 2. And that gives you another term. Okay, you just keep on doing that. You add all of those guys up, and that gives you what's called the variance, right? Now, it's a little bit hard to explain verbally, but basically this is the formula. This is the formula we're going to be using for our definition. However, as the author says, finding the variance by using this formula is tedious. So for just to make things easier on us, we're going to use a different formula that algebraically is equivalent. If you just did the algebra, you would find that this is the same result every single time. It is equivalent, okay? Okay, so as I've mentioned before, these blue boxes here kind of tell us what the usually is an algorithm or a formula of some sort. So to find the variance, okay, you multiply the square of, this is the square of each data point. So that's the X sub 1, X sub 2, X sub 3, X sub 4, and so forth. So you take the square of that, you multiply it times the probability of that particular data point. So it's X sub 1 squared times the probability of X sub 1. Okay, so that's inside the parentheses here. You sum those up. See, this summation sign refers to what's inside of this square bracket here. So you take each one of those guys, square it, multiply it times the probability of that guy. So the X sub 1 squared times probability of X sub 1. That's inside the bracket. So you add all of those up, and then you subtract mu squared. And then the standard deviation, of course, is just take the square root of that. Okay, so that Isn't that horrible? It does. You know, you look at that and you go nuts. Okay, you cannot figure out what the heck is going on. So, like I told you before, an example is worth 1,000 words. Okay, don't get stressed out trying to read this and go nuts. Go to the example and then take the example and apply it to what's in the blue box here, and you'll see it's not as hard as it looks. So let's take a look. Example 5-9, rolling a single die. Okay, we want to compute the variance and the standard deviation. It's the same example, or it's the same probability distribution that we had before in example 5-5. Okay, so we already computed the mean. That was mu is equal to 3.5. That was in example 5-5. We square each outcome, that's the x sub i's, square each of those, and multiply by the corresponding probability, sum those products, and then subtract the square of the mean. That's exactly what we're doing here. We take each one of those x sub i's, square it times its corresponding probability, add those guys up, and then you subtract the mean squared. So here we go. So it's 1, 2, 3, 4, 5, 6. Those are the outcomes. So this 1, that's my x sub 1. 2, that's my x sub 2. 3, that's my x sub 3, and so forth. So I take the 1, I square it, I multiply it times its corresponding probability, plus, now I'm adding, so now it's 2 squared times its corresponding probability, 3 squared times its corresponding probability, and so forth. So I add all these guys up. That right there corresponds to this portion of the formula. Then I subtract mu squared. There's the mu squared. There's the mu squared. So I crank that out and I get 2.917. So that's the variance of the probability distribution. Now to get the standard deviation, I just take the square root. So that's very, very straightforward, okay? All right, so now, I think this is a better example here. The thing I don't like about this example here, the rolling the die, is that, you know, I said this is x sub 1, this is x sub 2, and I'm afraid you're going to think, well, the x sub 1 and the 1, there's some correspondence there. There's, you know, but that's just a coincidence. X sub 1 happens to be the number 1. X sub 2 happens to be the 2. X sub 3 happens to be 3, but that's just a coincidence. So we don't have that problem here in this example. So I think this example is a little more clear, I hope. So selecting the numbered balls. You got 5 balls in the box. 2 are numbered 3, 1 is numbered 4, 2 are numbered 5. The boxes are mixed, or the balls are mixed. 1 is selected at random. You record the number, it's replaced, okay? So what's the chances of getting a 3? Well, in the denominator, it's always going to be 5 because that's how many balls there are. 2 are numbered 3, so there's 2/5. 4 is, there's 1 and 4, there's 2 5. So here's the probabilities. So you can easily compute the mu. Go crank that out on your own, and you can easily compute the variance. It's going to be just exactly like we did before using the formula, okay? Now, on this one, I'm gonna do example 511. I'm gonna do that in the next recording because unfortunately the author kind of made this unclear, or there's a typo. I'm not sure how you want to say it, but I'm gonna do this one in the next video. So we're gonna stop this video right now. Thank you.